I'm Carter Hawkins. I'm an intended aerospace engineer.
I'm Nick Patel. I'm aerospace intended.
Hi, I'm Nolan Canegallo, aerospace engineering intended.
I'm Rachel Roberts, chem engineering intended. Our whole time spent on the project followed the process that is outlined in the engineering design cycle. In order to start the project, we had to ask ourselves what we were trying to accomplish. The goal for the precision launcher was to successfully build a launcher that could consistently shoot a projectile at the center of a target that was 30 feet away. The next step was to imagine how we wanted our launcher to look and launch. We knew that we needed to incorporate a 5-pound weight to get the launcher to work, but the question was how. We went through several ideas before figuring out the final design. Our launcher, we decided, would utilize a drop tower for the weight and a system of pulleys to pull the projectile back for the launch. Once the type of launcher was settled on, it was time to plan out what materials we needed and how to actually build the projectile launcher. We needed lots of wood, some pipe, rope, and a few pulleys. The projectile would be a foam ball, and a piece of pipe that was cut in half would act as a guide for the ball so that it would be kept straight during the launch. After planning what all had to be done, we were ready to start building the prototype. The launching platform was made from screwing some PVC piping to a piece of wood, which was then attached to a larger piece of wood that would act as our base via some hinges. Our drop tower was a 3.5-foot plank of wood that was placed behind the launching platform, and several small chunks of wood were placed below the launching platform so that the angle of the launch could be changed. When the prototype was finished, we noticed that there were a few issues that needed to be fixed. The first problem was that the weight, when dropped, could not provide enough energy to pull the latex tubing back. The next problem was that the pulleys would rotate when we would fire the launcher, and it would mess up the rope, which then prevented the launcher from pulling the tubing back and firing. The solutions to these problems were to add a third pulley to our 2-pulley system so that the amount of force would be doubled, and to place blocks of wood around the rotating pulleys so that they no longer rotated.
Our team faced 3 main design challenges in the construction of our precision launcher for FEDD. The first was stabilizing the design. Our initial prototype had several stability issues resulting from the back-heavy design and the rope and pulley on top of our tower having too much freedom. We remedied this issue by shifting the drop tower to behind the platform, adding a second tower, changing the type of pulley on top of the tower, and securing the components to the platform more strongly. Our second design challenge was getting enough pull on the latex tubing. In our initial design, we'd only used the 5 pounds falling from 4 feet to pull back the tubing and store the energy to fire, and as a result, our prototype was unable to pull the latex tubing back far enough to fire. To solve this, we added a second tower and doubled the number of pulleys in order to gain a mechanical advantage and turn the 5 pounds of force over 4 feet into 10 pounds of force over 2 feet. Our third design challenge was release of the firing mechanism. A big problem we found after working with our second launcher was that it wouldn't fire properly when we replaced the wooden catch on the mechanism with a bolt. Our solution was to use a bent hinge with guide blocks as a knock, wrap the threads of the bolt with dense material and tape, and add some worn sandpaper to the back of the hook to help prevent early releases or misfires. You can see the results in the videos to the right.
So how did we do at FEDD? Well, we came in first place, outscoring second place 120 to 50. The launcher worked surprisingly well, with the firing mechanism working consistently and the projectile firing over 30 feet on all 3 launches. Our first shot was fired from 25 feet, which we had found to be our maximum range in testing. To our surprise, the projectile fired way over the target and slightly to the right. We moved 5 feet back to 30 feet for the second launch. The launch was perfect, with the projectile flying straight ahead. However, the projectile again went over and past the target, meaning we were still too close. We moved further back to about 33 feet for the third and final launch. It was another smooth launch, and this time the projectile hit the inner ring on the target.
Now, some things we wish we had done different would have to be getting a working prototype. Due to time constraints, we weren't able to get the prototype to work before eventually deciding to spend our time on the final design. We had tried testing the prototype, but came across issues that wouldn't let it launch, so we decided to fix those issues on final design rather than getting our prototype to work. Another thing we would have done different is to test the smaller individual portions of the launcher. We simply put all the pieces together and then tested it, but there were issues with the individual pieces that could have been dealt with before the entire launcher was built. So my advice to incoming freshmen would be to meet more often than you think you need to, because there's going to be some things that come up, and so you're just going to need to meet more often.
My advice to freshmen would be to start earlier on the prototype so that you have more time to refine the project.
My advice to incoming freshmen is to plan your meetings at the craft center in advance so you can book your times.
My advice to incoming freshmen would be to not put this project off because the work will pile up and you'll have a lot left to do and not a lot of time.